Hello everyone! In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will examine our first distinction between classes of elementary particles, the difference between fermions and bosons. So in the first video, I gave a brief description of the standard model of elementary particles, and there are many bits of vocabulary and many ways of divvying up this group. And so the first distinction we're going to examine is the difference between what are known as fermions and what are known as bosons. So fermions are a certain class of particle. They can be either elementary or what is known as composite. So elementary particles are the most fundamental particles that exist. Composite particles, including particles like the proton or neutron, are actually made up of other particles. So elementary or fundamental here means cannot be divided. It's the original atom, if you will. These are indivisible particles. There's nothing that they are made up of, and composite particles are made up of several particles. So fermions can be both, depending on the situation, but most importantly, fermions cannot occupy the same physical, read quantum here, so the same physical state. They obey what's known as the Pauli exclusion principle. And most particles that we're familiar with, although not all, are fermions. They cannot physically be in the same state. With electrons, those of you who've taken some chemistry can probably remember drawing sort of spin up and spin down, sort of ways of filling those orbitals. The fundamental instinct that we have that matter, a fundamental particle, cannot be in the same physical location as other matter, is related to this idea, this fundamental principle of fermions, that they cannot occupy the same physical state. A proton cannot literally be in the same location and with the same properties as another proton. Same for electrons. And they have what is known as half-integer spin. So that spin up or spin down, those arrows that I pointed to, are related to a fundamental physical property known as spin that is sort of loosely related to angular momentum. So this sort of, you can visualize it incorrectly, if you will, as sort of a particle spinning on its axis in one direction or another. That is a very, very loose description of how spin works, but it's probably good enough for our purposes. The vast majority of particles that you are aware of are fermions, and they are what we think of as physical particles and of matter. Bosons are a separate class of particles, and they can occupy the same physical state. They can be elementary or composite, and we are at this point familiar, or you might be familiar with two of them. One you probably know, but don't know what it is, which is the Higgs boson. The other you know, but didn't know that it was a boson, which is a photon. So think about the fact, for 1 second, that photons, right, if you shine sort of two beams of light through each other, notice they don't run into each other. They don't run into each other in that sort of way. They cannot... they can be in the same physical state at the same time. Think about the way we think of electromagnetic waves as superimposing on one another rather than colliding. This is the fundamental idea. And the photon, as a particle, considered as an elementary particle, has integer spin rather than half-integer spin. This is sort of the fundamental property that makes it a boson. But because we're not going into the math, you can think of it as being fundamentally related to this idea that they cannot occupy the same, that bosons can occupy the same physical state. And we're going to see as we go through them a number of those particles, including the photon, the W and Z bosons, and the Higgs, as well as some composite particles that are bosons as well, known as pions and kaons and others. Bosons also include what are known as the gauge bosons, which we will see a little later. Gauge bosons are particular bosons that are the force carriers for the different interactions. The electromagnetic interaction has a force carrier or interaction mediator of the photon. The photon is what sort of carries the information about the electromagnetic interaction from one particle to another. The W and Z bosons, which we'll discuss more, are the weak interaction force carriers, and the gluon is the strong interaction force carrier. There is a hypothetical particle known as the graviton that is the interaction or force carrier for gravity, but it has not yet been experimentally confirmed, so it is not on this list.